Hello, everyone. My name is Zahra, and my talk today is going to be about enabling hardware-assisted shields for hardening Linux security subsystem, which is not an official Microsoft product. It's basically on a research state for now. A bit about me. My background is mostly in systems and security. I got my PhD from University of Cambridge System Research Group, where I mostly worked on hardware-assisted compartmentalization and confidential computing, and basically systems abstractions for better defense in-depth mechanisms. And currently at Microsoft LSG team, I'm working on related security-related topics. So let's get started. First, I will discuss a scope of the project. Basically, try to explain what is the actual problem we are trying to resolve here. Then I will explain some of the technical background for some of the components we rely on, and then I will discuss hardware shields abstractions, the abstractions that we are adding to the kernel with different like hardware or the hypervisor backend. And they will conclude this talk with discussing some of the current limitations for the current prototype and the future work and some of the opportunities for collaborations. As you know, a secure operating system is essential for keeping the entire systems and all of our applications in a secure state. Yet our operating systems are still vulnerable to many different attack vectors. Because of their monolithic design, because of their complexity, or because they're written in unsafe languages, and so on. A recent paper, actually, that is cited here, investigated the existing attacks on Linux kernel. And their security analysis shows that most of these attacks, about like more than 75% of attacks on the kernel, are related to memory safety issues and also lack of proper privilege separation. So this is actually the majority of attacks on the kernel. But this is a very hard problem. It's still an open problem on systems communities to enable proper privilege separations on a monolithic systems, or like having a proper OS hardening. But we had amazing progress on control flow integrity techniques and fuzzing techniques, but these are still not enough. Good news is that the recent hardware features for better, more efficient privilege separation, for basically better memory, better targeting memory safety issues like pointer authentications, like tagged memory, introducing memory protection domains, and these features are helping existing privilege separation techniques to be more efficient, so we can scale the security solutions on the kernel. Hypervisor-based security is actually one of those techniques that is very old. Is used for all kinds of security checks on the operating system, because well, hypervisor is running on a higher privilege layer, and it can be really useful for deprivileging the actual operating system, for enforcing address space protections of the kernel, for verifying image integrity, for UEFI protections, for even kernel module protection, and all kind of monitoring attacks from the kernel side. But since they usually add a lot of they were usually adding a lot of performance overhead, they're not used that much for fine grain privilege separation on the kernel, or for more dynamic kind of security features. But recently we see that with better hardware virtualization support, we see these kind of techniques are getting more attention. These are getting like more practical. That can be even used for more dynamic sort of like monitoring or enforcing like security checks. So that's why like we see more progress on like different kind of hypervisor, for example, like Hyper-V, like adding, introducing like virtual trust levels, and that Windows VBS have support for all kind of like security features like credit guard, like device guard, and all kind of this kind dynamic also security features through Hyper-V. We also had Heki introduced like by Mikhail recently, and Zen for a long time like has this more kind of dynamic memory protection features, giving you like different view of address space, so you can have some sort of better compartmentalization features on Zen through Alt P2M feature that they have. So hypervisor-based security is getting like more practical now because of better hardware that we have. On the other hand, we also see more fine-grained, like hardware memory isolation features, memory protection features to our platform. One of these cases are like ARM Morello architecture that is basically extending existing ARM 64 architecture, like V8.2, with CHERI hardware capabilities that are basically like adding hardware-based metadata to every pointer for assigning permissions to that protected capabilities, to assigning object types, to making sure that every region like bounds checking are like hardware based, and these capabilities can be used for like scalable compartmentalization and the system from bottom up. So they extended the existing architecture, ARM architecture, and all of the instructions, like for example, for load, store, execute, all of these, like there is also a capability-based version, load capability, like store capability, with some additional capability on the instruction, for example, for sealing, like making a capability immutable. And all these extensions are also added in every privilege layer in ARM. So for example, in the secure mode, you can also have compartmentalization. So for example, the secure world that we already had, for example, trust on architecture, it was a one-way trust between the secure world and normal world. Now you have kind of mutual you can have the mutual distrust between the regions. So there is a lot of possibilities for better privilege separations and systems now. So both of these techniques, these approaches, virtualization-based security and these kind of hardware-based finer grain protection features, these are can complement each other. And there are privilege separation solutions based on both of these solutions. And for hardware shield abstraction, we were looking at the state of the art for these two approaches, and we want to have the abstraction that is providing a minimal security primitives that can be used in an extensible and a scalable way for hardening Linux kernel security subsystems such as SE Linux, like EMA, like LSMs and eBPF. And we were looking at what are basically these minimal primitives that can have a different backends. It can the enforcement and the isolation. It can happen with virtualization based security, and when it's not efficient anymore, when it's it's more useful and we have a better hardware, finer grain hardware protection like CHERI, or memory tagging features like MT, PAC, protected authentication, we can then switch to enforce the actual isolation through those features. And this way we can have a scalable and more kind of practical solution that we can find the right balance between performance and security. So between these like primitives, the main thing in common is like memory isolation, like that can be provided with both of these approaches. Then there is code and data signing and authentication. And then there is the concept of like a compartment, the domain of like isolated execution, and the abstraction for managing this kind of domains. So hardware shields are going to provide these abstractions, common abstractions, but the enforcement, the isolation, can be provided by either like visualization-based security or like finer grained like hardware protections like CHERI or MT or PAG. So for early prototype, the first attempts to actually find out like what this abstraction is going to look like, we target CHERI ABI for ARM64 based kind of like platform, and HECI like hypervisor-based kernel integrity features on KVM for x86 and 64. The reason for these two completely different like designs and like different security architectures as Shield's backend is that well, CHERI on ARM is providing us like with a kind of a scalable compartmentalization and privilege separation by design. So we don't have like the like limitations for the number of like isolated like regions. We don't have like, for example, the limitations that we have if we pick MT or PAC pointer authentication on ARM. There are limited, for example, like tags available for coloring and here with CHERI, we have kind of like that environment that we can um, define what would be an ideal kind of state for our privilege separation mechanism. And on the other hand, for like x86, between different kind of like hypervisor-based securities, unlike Hyper-V and like Zen and HECI. We pick HECI because like the difference between like Zen based and Hyper-V based and HECI is that Zen and Hyper-V like they define like explicit like trust domain, like domain DOM0 based or like a VTL1, for example, secure kernel in Hyper-V. That in those domains you can like basically those are your like secure kernel. You define all of the security specific primitives there, and like then you need to like interact with that kernel. So that it's a very explicit like trust like level between the hypervisor and that secure kernel and your like operating system. But HECI, since it's a KVM based like enforcement, it's kind of like it has a different architecture, but still it provides like the memory protection and like module based like isolation for the kernel and all of these features. So we thought like if we have a like if we can find like a better security interface that also works with HECI, it's gonna definitely work with like other kind of like virtualization based security. So these two can give us like a good way of like view from two different kind of architecture, two different designs for coming up with like what are these like minimal security primitives that we can like implement on shields for like a scalable and extensible like privilege separation that can be used for hardening like Linux security subsystems. So the first primitive that we need for shield is memory protections, like the abstraction to basically define like which parts of the kernel address space should have like which kind of permissions, and the enforcement, the isolation should be protected by like the hardware or the hypervisor. So this is easy, like because both like hypervisor-based security like HECI and like Morello, like CHERI, this is the first like primitives that they all support. So we just needed to provide a wrapper around like their functionality. So we added like a wrapper of shield protect address that basically on KVM based platforms, it uses key protect memory like hypercall, and on Morello it's basically using CHERI instructions for like address set, for bound set, and assigning the permissions, and then that region is protected by CHERI capabilities. So we need this like as the main building block for the isolation of the shields. And this actually memory protection, the first thing that is being used, like when you have the memory protection, we assign like a specific hashes, signatures, and software-based kind of capabilities that I describe later. And all of these like security sensitive like metadata and things that we need for like other primitives for code signing, data signings, and these are needed to be protected by this memory protection feature. So we first need this building block to store all of the security sensitive metadata that we use for other primitives to be protected like as read-only and protected by hardware or the hypervisor. The second primitives that we need for shields are code and data signing and authentication, because isolation itself is essential. For example, for SLinux policies, we want to isolate the policy, but we also need authentication mechanism to measure the integrity and make sure that this policy is not modified, and provide the proof for that. Shields implement a very few set of signing authentication functionalities for pointers, for values, and for code regions. And all of these functionalities are also tied to a specific random context tag. We call it shield tag per privileged task struct that is basically part of kernel task that is assigned when a task is actually using shields. So this part is actually may change in future if we have a better way of having a authentication for user space tasks that they use shields. But for now, we're having this tag per privileged tasks. And internally, these functionalities are also using kernel zip hash, short input hash. And the values that measurements and all of these are marked as read-only true, the previous memory protection abstraction that we talked about. So for KVM, there is new hypercalls for doing this operation and also marking the result as read-only. And for Morello, we actually have this sealing capability for making the values immutable. And we also have signing and authentication capabilities. That's only with those capabilities you can do these operations and store basically the values to protected, read-only protected parts. So the third primitives is that the concept of an isolated execution unit or a compartment or protection domain, and all of the management abstractions for that is still going to be a future work. It's not developed. We don't have a prototype for that. But even with the memory protection and the authentication and signing primitives, we can start improving the security of our current security subsystems like SLinux. For example, for SLinux, we have this new security SLinux shield option. It's a mode of execution that when you are in that mode, for example, shields are going to avoid any kind of mode, SLinux execution mode for from enforcement to permissive or disabling it. It's also using shields memory protection and like also authentication to make sure that the policies, like Linux policies, are read-only with ABC cache as well, and all of like internal like basically sensitive data structures like Linux policy, map, and hash. All of these are also like protected by shields that the backend can be like different backends. For prototyping on like CHERI, that's basically our first like implementation. We used Morello Android kernel for that. We extended like the Android kernel for with these primitives, shells primitives, and because like for on Android we could have Morello based like compiled libSlinux. They basically you need to like have a cross compile with a specific CHERI like compiler and things like that. And for now, I haven't tested like anything on real ARM real ARM with FVP. But it's a very good development environment. It's a little bit slow with but on FVP, for example, like if you go to like Morello project and you have a simple script with initializing the FVP with Android software stack, and then you can have like a very kind of easy development environment for that. So since this is a short talk, I'm not going to more technical details now. Just note that there is still a lot of things we need to do, and this is like an earlier stage project, especially from like user space API. We haven't implemented that yet, and it needs to be really secure because we don't want to open up new attack vectors for attackers to launch even stronger attacks, like by misusing our privilege operation, by misusing our like interactions with the hypervisor. So we plan to implement that like on Rust, and also like make sure that all of like the intersections are like logically and also like from implementation perspectives are secure. Also, we need to after we got feedback from the first patches, we need to think about the integration with other Linux security features, like for hardening eBPF, for example, or seccom and things like that. Similarly, there are other hardware security features that can be integrated to shields. For example, PKS, like protection domains on supervisor mode for Intel. That basically Intel actually has a prototype for using that for hardening eBPF like verifier. So integrating things like that, or using like MT and PAC on ARM devices when there is no CHERI available. These are important future works that we can like implement better privilege separation tools for Linux kernel. With that, I'm happy to take any question. Please contact me if you need more details, and if you have any questions. And thank you for your attention.